till now what did we study? We studied that stator consists of one winding, and again we are going to give AC supply to this, and AC supply is alternating type. Again that alternating type will create pulsating flux or pulsating vectors, and due to that what happens, the resultant flux will be always zero, right? Always zero unless or until you give a twist in either forward direction or backward or anti-clockwise direction. The motor will supposed to flow or supposed to rotate in that particular direction. Yes or not? Yes. And now we shall see, instead of giving twist and all, what if we make some special arrangement such that motor will self start by itself with that special arrangement. So here we have some types of single phase induction motor. The first one is split phase, the second one is capacitor start, capacitor run, whereas fourth one is shaded pole induction motor. We shall see all of this four things separately. So before knowing all these four, first you should learn this split phase induction motor very carefully. Now let us understand why we are calling it as split phase induction motor. Earlier till now what we studied, there was only one winding or one main winding in the stator. Now what I will going to do is, since to produce a rotating magnetic flux instead of having pulsating magnetic flux, so what I am going to do is I am going to add one more winding in my stator part. Okay, I'm going to add stator part. I'm going to connect the other winding to the AC supply. So one will act like a main winding, the other one will act like a starting winding. Okay, now the one which winding I've added is also called as a auxiliary winding, in contrast to that main winding. Okay, and again make sure the main winding and your auxiliary winding are what, 90 degrees to each other, okay, in space. Now what happens, before I told that there was only one main flux, but here what is happening, now you are having two fluxes. One flux is produced by main winding and your second flux is produced by your auxiliary winding. So these two fluxes will interact each other so as to produce a rotational magnetic field. Okay, so here you can see that phi 1 is the flux produced by your main winding and phi 2 is the flux produced by your auxiliary winding. Again you can see there is a difference of angle alpha. That's what I said, you can have even 90 degrees also, but since just for sake of understanding sake, they are just representing the phase difference between those two fluxes as alpha. Okay, remember, more the alpha, more the starting torque is. So starting torque or torque is proportional, directly proportional to the alpha angle. If alpha is more, the starting torque is also more. So due to this what happens, addition of auxiliary winding in the stator winding to the existing main winding, placing 90 degrees apart, that converts pulsating flux into rotating magnetic flux. Okay, so what happens, there creates a phase difference between two fluxes, and that phase difference will make the pulsating into rotating one. Okay, now let us take the first one, split phase induction motor. So this is the diagram of split phase induction motor. That's why I told you one winding in the stator is main winding, another winding is starting winding, and what we have a phase difference of 90 degrees electrical and space. Okay, now you can see the current flowing through the main winding is called as IM, the current flowing through the starting winding is called as I start. Okay, only I told you only this winding will help only during starting. After that we don't need this. Okay, the one thing what we have here is centrifugal switch connected in series in the starting winding. So what I do is, I'm going to connect the supply. So what happens, current starts to flow in the main winding as well as current starts to flow in the starting winding. The flux due to IM as well as flux due to IST will interact each other and cause what, a rotational magnetic field in the stator that causes the rotor to rotate. Once your motor achieves around like 50 to 60% or 70 to 75 to 80% of the rated speed, what happens, this centrifugal switch automatically will open. Initially actually it will be closed, Initially, normally it is closed. When your motor reaches to 75 to 80% of speed, the centrifugal switch get open. When it get open, what happens? The starting winding will be no more electrically connected. So IST will be 0, only current IM will start to flow. And that unbalance will be created by starting winding. Before I told, right? Before I told you create unbalance either by twisting the rotor in any one direction, clockwise or counterclockwise. But actually what happens? You don't do that. The machine takes care of that by having some special arrangement, that is adding starting winding in 90 degrees to the main winding. Okay, so once a twist is created, no need to again create the twist. That twist is carried forward, so your machine will start in that particular direction. If you want to change direction of that machine direction, what will do, either you will interchange the main winding, or you will interchange the starting winding. Okay, the centrifugal switch will only open when your machine attempts to 75 to 80% of the rated speed, depending upon the design. Okay, see, this is how the stator part, this is the rotor, and this is the main winding, and this is the starting winding. Both are 90 degrees electrically apart. Now we shall learn or understand in terms of phasor. Let V be your reference diagram, voltage, and we know that this main winding is inductive type, highly inductive type. You can see IM, the current which flows in this winding is IM, and again you can see, we know that inductive type, what happens, voltage always leads the current, or you can say current always lags the voltage almost equal to 90 degree. You can see IM is almost equal to 90 degrees to the voltage, supply voltage V. And you can see that starting winding is less inductive, it is not that much inductive that of main winding. So what happens, you can see starting winding, due to the small inductive nature, IST is the current which flows in the starting winding, is lagging the voltage for certain angle here. Okay, though angle is not mentioned, but you can see IST is lagging the voltage by certain angle, since it is less inductive when compared to H. Okay, now what happens, you can see IST is here, IM is here. Again, phi m is the angle between V and IM. Again, alpha is the angle between IM as well as IST, the earlier phasor diagram which we studied here. Okay, phi 1 and phi 2. So that is what the alpha angle is, IM and IST. Alpha is the angle between IM and IST. So as alpha increases, torque increases, the starting torque will also increase. Okay, the resultant due to IM and IST is I. Resultant due to IM and IST is I. And this I, what happens? This is the rotationary magnetic field created due to the interaction between main flux as well as the auxiliary flux, or main winding as well as starting winding in the diagram. So this OI, whatever you are seeing, I, this will rotate clockwise direction like this. This, whatever flux I'm showing here rotating, is in the clockwise direction. This is the rotational magnetic field created in the stator, and this causes the rotor to rotate. It may be anti-clockwise also, it's not wrong in saying it is rotating in the anti-clock, depending upon how we are connected the main winding as well as starting winding. This is how the pulsating one is converted in terms of rotational. Just see, if the starting winding is not there, means IST would be 0. Yes, if IST is 0, then what happens, this I would be overlapped on IM itself. Yes, I would be overlapped on IM. I is the resultant due to IST and IM. Since IST is 0, so I would be overlapping on IM. IM and IM would be the same phasor. Again, this would be pulsating like this, up, down like this. Okay, this is not rotating. We don't say this is a rotating one. This is a pulsating one, up and down. This makes rotate only when we have auxiliary winding, and resultant both flux will create one more resultant flux, that is phi, main flux phi, and this flux will rotate either in clockwise in space or in anti-clockwise in space, depending upon the connections of the starting winding as well as main winding. So you understood how the motor runs. Okay, this is what we have, the split phase induction motor. Okay, and this is the speed torque characteristics here. Okay, again here it says that it has a pore starting torque as around 125 to 150% of the full load torque. Okay, this is the speed torque characteristics, similar to that of earlier torque, speed torque, torque characteristics. Okay, speed, you can see speed, if you draw like this, speed decreases. Okay, this is the starting torque. Okay, otherwise when n is equal to ns, it's only possible when slip is equal to 0, and n is equal to 0 possible only when slip is equal to 1, right? Now we can see capacitor start induction motor. Again, we have two types of motor here. One is capacitor start motor, one is capacitor start capacitor run motor. So we shall see first capacitor start motors. Okay, you can see it is same bed of split phase induction motor. Only one thing what we are doing is we have added capacitor in series with the starting winding. Yes or not? Okay, and also we have a centrifugal switch. So similar here also, when I give supply, IM and IST flows, and IM, as we said that this main winding is highly inductive. V and IM will be approximately equal to 90 degree, but here they have shown certain angle phi m. But you can see that starting winding, it is a less inductive one, like I said before, and this IST flows in starting winding as well as capacitor as well as centrifugal switch, and it completes the path. And we know that current flowing in the capacitor, what happens? Current leads the voltage, yes or not? So this and this both will act like a capacitive type, not 100% capacitive, can call nearly capacitive. What happens here? This IST leads the voltage. You can see IST leads the voltage, yes or not? It's leading by certain angle phi st, and again IM lags the voltage by phi m because it's an inductive, and this both will make capacitive. So IST leads the voltage by alpha. Now you can see IST and IM are what? Alpha is increased, yes or not? Alpha was little here, alpha was small here in the earlier diagram, but less than 90 degree, but here it is almost approximately equal to 90 degrees. Like I said, alpha increases, torque will also increase, yes or not? So here torque is high when compared to that of your split phase induction motor, which creates again IST and IM results IA. This also will rotate what? In the clockwise direction or anti-clockwise direction, depending upon the main winding as well as starting winding connection. So thus converting pulsating into rotating one. And here also centrifugal switch is there. Again, initially it will be normally closed. When your speed attains 75 to 80%, what happens? The centrifugal switch gets open. Then what happens? IST becomes 0. Again, that twist is carried forward and machine will start to run by itself. Okay. So this is what we have. So that's why it is called as capacitor start induction motor. Now here, let us see capacitor start as well as capacitor run induction motor. Here we don't have any centrifugal switch. Same thing happens here. I supplies voltage, will supply I will supply IM and IST. Again same, IM will lag the voltage by certain less equal to 90 degree, and IST will lead the voltage by same thing, same phasor we can have for this diagram also. This is diagram for capacitor start, capacitor run. And again, so here also what happens? Alpha is created between IST and IM with same you can draw for this also, capacitor start, capacitor run. Again I is created here, that is resultant of IM and IST, that is also rotating in the clockwise as well as anti-clockwise, depending upon the main winding as well as auxiliary winding connection. And here we don't have any centrifugal switch, so your auxiliary winding will be intact throughout the operation, no any opening or no any closing the switch. Okay, so your machine will be having even more proper, can say, constant torque depending upon the voltage you supply. Okay, so this is how your capacitor start, capacitor run induction motor runs. Okay, remember there is a squirrel cage induction motor here. This is not a slip ring induction motor. As I said, we don't use any slip ring induction motor. The construction of the squirrel cage induction motor is, or rotor is, very simple when compared to that of your slip ring induction motor type. Okay, and again we have here torque speed capacity characteristics here. One which we have drawn here is the capacitor start, and the second one is what we have, what capacitor start as well as capacitor run. And here you can see capacitor start, we have starting torque is high, so not starting torque is high, whereas capacitor start, capacitor starting torque is less when compared to this. Okay, the same, the format of the diagrams will always remain same, just a point below. Okay, you can see again this type of motors, capacitor start, capacitor, are used in what? Air circulator, ceiling fans, blowers. Yes, the one which rotates above head, ceiling fan, such type of motors are used. Capacitor start, capacitor up to 6 kilowatt. Okay, and even they are used in compressor, conveyors, grinders, fans, blowers, refrigerators. So try to remember these applications, it will help in your examination.